Hello students, today we're going to be taking a look at section 6.8, Rational Zero Theorem. Identify rational zeros. To start, the rational zero theorem states that letting f of x equal a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 and so on all the way until we get to a sub 0 represent a polynomial function with integral or integer coefficients. If p over q is a rational number in simplest form and is a zero of y equals f of x, then p is a factor of a sub 0 and q is a factor of a sub n. We're going to be talking quite a bit about p over q today, and in the context of how the factors will divide out, p being the factor of the a sub 0 term, which we said earlier was the constant or last term of the function, while q represents the factors of a sub n, or the leading coefficient aspect. A corollary to this, the integral zero theorem, or integer zero theorem for that matter, if the coefficients of a polynomial are integers such that a sub n equals 1 and a sub 0 does not equal 0, any rational zeros of the function must be factors of a sub 0. For example, list all possible rationals of each function. So to start with, part A, f of x equals 3x to the fourth minus 2x squared plus 6x minus 10. If p over q is a rational root, then p is a factor of negative 10. So this is your a sub 0, that constant that is, and this is your a sub n. So as it states, p, and really p is just a representation of the last term factors, that of course again being negative 10, and then q a representation of the coefficient and those factors respectively. So the possible values for p would be plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10. Again, think of the idea of what numbers multiply to give us 10, or technically negative 10. As it turns out, 1 times 10, or possibly, 1 times negative 10 is a possibility, but so is negative 1 times positive 10. So 1 times negative 10 or negative 1 times positive 10. Same goes with 2 times 5. 2 times negative 5 is an option, but so is negative 2 times positive 5. Again, those are factors of negative 10. The same holds true with 3, and I believe this is a typo. Actually, this should actually be a plus or minus here, and a plus or minus there. Okay, so we have plus or minus 1 and plus or minus 3 as the possible factors, or the factors really for the constant and the the coefficients. Excuse me. The constant term is negative 10. The coefficient is 3. So plus or minus 1, plus or minus 3. So all of the possible rationals will now be written as p over q. Simply divide plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10 over plus or minus 1 and plus or minus 3. If you do that, you'll have 2, 4, 6, 8, 10, 12, 14, 16 possible rational zeros. And they have to be framed as possible rationals as opposed to actual rationals, because technically, remember, this function is a fourth degree. As a fourth degree function has been viewed in the past, and as we know from the past, a fourth degree function can only have 4 zeros. Yes, they could all be imaginary. You could have 2 imaginary and 2 real. You could have all real, of which are rational, but 4 reals / rational, if you think about it, would then suggest that out of the 16, 12 of them don't work. Because, of course, if 4 are rational, 12 out of the 16, well, can't technically be answers. And that's what we're going to be testing eventually. We're going to be testing to see if out of these 16 possible rationals, which ones are good answers or actual answers. Part B, x cubed minus 10x squared plus 14x minus 36, wherein we can see here as your a sub n, there's your coefficient, your leading coefficient, while this is your a sub 0. Since the coefficient of x cubed is 1, the possible rational zeros must be the factors of the constant term negative 36. So really it's p over q, but in the sense where, because in this case q is 1, the factors of 1 are really just, I guess, plus or minus 1 technically. You're just going to look at negative 36. So the factors of negative 36 are plus or minus 1, plus or minus 2, 3, 4, 6, 9, 12, 18, and 36. So that's 2, 4, 6, 8, 10, 12, 14, 16. That's 18 possible rational zeros. Out of the 18 that are possible, think of it again as we saw in the last example. Out of the 18, technically, because the degree is 3, only 3 will, if they're rational, be actuals, let's say, or in fact work. So that would indicate that 15 would not be reals, or rationals, pardon. Speaking of reals, though, and also imaginaries for that matter, it is very possible, because it's a third degree, that you have 2 imaginaries and 1 real. And that real could very easily be rational. So then 17 of the 18 would not be actual solutions. So we're going to go ahead and move on. We'll take a look at a couple of these questions. I believe, if we take on number 1 here right off the bat, listing all of the possible rational zeros, we should be in good shape. So with respect to, yet again, just simply identifying your a sub n and your a sub 0. Okay, like we saw up top, we'll do our p over q analysis. Okay, so p over q is as easy as finding the factors of one divided by the factors of another. Okay, so we always put in the numerator the factors of the constant term. So we've got plus or minus 1, 2, 4, and 8. Okay, and I'm going to write it as a fraction so you guys can actually see when it's all said and done how the fractions and or rational values just come about. So again, those are the factors of 8. While the numerator, the denominator using the coefficient, the numerator over the denominator here looking somewhat like that. Okay, so that's another way to kind of think of it. And because of the nature of what the leading coefficient is, the answers end up simply being plus or minus 1, 2, 4, and 8. So that's how I list it, and that's really all I need you to do on those types of questions. If the denominator wasn't 1, which we're going to maybe take a look at here at another problem in a moment, if the denominator wasn't 1, then you're going to have to write out all the fractions separately, similar to part A as you see up above. Okay, so let's do that. Let's take on number 5. So in number 5, we've got a leading coefficient, a sub n of 3, and we've got a constant a sub 0 of 12. So if we do p over q, again, the values for both, the factors for both, and I apologize, I need to squeeze in q on the last problem because I didn't do that. So the factors, again, of the a sub 0 term end up being what? Factors of 12, so 1, 2, 3, and I'm probably going to have to move this. Pardon. And let's do plus or minus 1, 2, 3, 4, 6, and 12. All of those divided by the factors of 3, which are plus or minus 1 and plus or minus 3. And again, if you're wondering why we're doing plus or minus, think of it again as when you divide a negative by a negative, you're going to get a positive. Or a positive over a positive, you're going to get a positive. So if your goal in the end is to get answers that not just dividing per se, technically, because they could be negative or positive when dividing, but certainly when you are finding, let's say, I don't know, the factors such that what, 1 times 12, yes, in fact, multiply to 12. But what if one was negative and the other was negative? Negative 1 times negative 12 is positive 12. That's the idea that you want to kind of keep in mind as you're doing this. So let's finish this. I do want to kind of showcase the full fractions. So 1 divided by 1, but also 1 divided by negative 1. So you have plus or minus 1. 2 divided by 1, 2 divided by negative 1, plus or minus 2, and so on. So that's going to be true with all of the numerator values, such that all of those are just pretty much exactly what we started with. What is going to differ, though, is now when you look at dividing by 3. So plus or minus 1, plus or minus 3, dividing those two, you have 1/3, but you also have negative 1/3. Similarly, 2/3, negative 2/3. 3/3, negative 3/3. Actually, that's plus or minus 1 again. 4/3, negative 4/3. 6/3, negative 6/3. Yet again, that's 2 and negative 2, plus or minus 2. As is 12/3 and negative 12/3 being plus or minus 4 again. So that's 2, 4, 6, 8, 10, 12, 14, 16. It's 18. This time I'll write it on this problem, unlike what I didn't do necessarily on number 1. There's 18 possible rational zeros. I'll make the statement yet again, though. Because they're possible rationals, and also because there's a degree of 4 to start with, out of those 18 possible rationals, only 4 may theoretically work. So it turns out that the possible rationals are not actuals, hence the name. All right, let's move on to the next page. It does describe here finding rational zeros, and it's going to showcase yet again the P over Q concept. From the corollary to the fundamental theorem of algebra, we know that there are exactly 3 complex roots. So I'm kind of jumping in here where the degree again, because it's 3, we know we can't have any more rationals than the degree speaks to. But again, with regards to P and Q, here's your A sub n, here's your A sub 0. We are not going to use Descartes' rule of signs here, but because though we have 3 roots that we're shooting for or striving for, and also because we've got our P over Q taking shape as such, we've got plus or minus 1, plus or minus 2, 3, 4, 6, and 12, but also we have plus or minus 1/5, 2/5, 3/5, 4/5, 6/5, and 12/5, again dividing P, the factors of A sub 0, over Q, the factors of A sub n. So these are the 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24 possible rationals. Out of the 24 possible rationals, we can only again have 3 that actually work, and heck, we might only have 1 that works because 2 of them are imaginary. If you do the analysis as they describe, now this is a matter of maybe them shortcutting the actual work of synthetic division. I would argue that you should do synthetic division in full, so that you take 1. Which they're describing here, f of 1 is equal to 0, which by the way is one of the numbers on the list. There's 1 on the list. So we do that with 1 and of course 5. When you do synthetic division, 12, negative 29, 12, you should end up with a remainder of 0. I'll just prove that out here. Okay. So of course we get a remainder of 0, wherein then this resulting quotient is your depressed polynomial. And yes, that depressed polynomial may or may not be factorable. In this case it is factorable, as you see, which suggests that you have 2 more zeros. If you set this equal to 0, you'll end up with x equals 3/5, but also x equals negative 4. That is also indicative back to the list, such that 3/5 is an answer. Here's 3/5, and so is negative 4. Synthetic division should still be established when you're doing these problems, so please do that when you're doing that type of analysis. Example 2, I ask that you try that on your own and make sure that you compare your kind of version to the notes that I complete at a later time. Thank you, and please complete the homework for today as well.